Thank you very much to the organizers for inviting me to this already wonderful conference and a wonderful place to which I had never been. Thank you for the previous two speakers for setting up a couple of things for me. No worries. No, thank you. So this is mostly joint work with Paul Balmer over the last maybe 5 years. If I don't say it, it's probably a joint result or a joint definition that I will mention. Occasionally, other people will pop up. And it's about Mackey 2 functors and Green 2 functors. So I will give you maybe the general idea. It's about doing representation theory of finite groups. So there will only be finite groups here, but you can extend things in many directions, including non-finite groups. But there is something essential. I mean, there are lots of complications which are already apparent here in the case of finite groups, so that would be enough. So classically, this is a theory which was born in the early 70s in an article of A.J. Green, then Andreas Dress and Lindner, essentially, and then it took off, and many people used Mackey and Green functors and similar things. So the words Mackey functor and Green functor, I'm going to use them in this original meaning at first. So a Mackey functor should be some algebraic gadget which is an equivariant version of an abelian group. And a Green functor is the associated equivariant version of a ring, so an associative unital monoid. Okay? And now, what does equivariant mean? Well, we want to axiomatically capture in these gadgets all the restriction, conjugation, and induction, or often called trace maps, which you find throughout equivariant mathematics, especially originally in the linear representation theory of finite groups. Think group cohomology, think character rings, algebraic K-theory, equivariant K-theory, okay? All sorts of stuff. Now, since then, many versions of these notions have arisen and have been used. I should mention some derived version. In particular, the spectral Mackey functors and also spectral Green functors, in the sense of Clark Barwick, and his many collaborators. That's because, so one of the sources of Mackey and Green functors is topology, or equivariant topology. So most of you probably know that if you take a genuine G spectrum, its homotopy groups are naturally a Mackey functor for the group G, an algebraic one in the original sense. But sometimes you want a bit more structure and so on, so you need fancier definitions. But today, today our goal will be to basically categorify the original notions, but only one step, remaining in the world of two categories, or bicategories. It will be equivalent, it will be the same for me today. So using only two categories, where we replace an abelian group by an additive category and a ring by a monoidal additive category, where the tensor preserves direct sums. And so the thing is, our theory should be easy. So it should receive examples from the fancier, higher categorical versions of this, but it should remain, hands-on, algebraic, finitely many axioms, so no model structures, no choices of models and stuff like that. And there is an advantage to that, because up to two categories, as you probably know, sometimes three, you can do things in a coherent way by structifying, and there is a way to do this. Then after that, you better go all the way to infinity. But so there's an advantage to remaining simple. Also, because then you can explain things to people who do not know any topology, right? No, seriously. It's not the case today, but so usually when I give a talk about these things, I have to say, probably this is on the abstract side. There are higher categories. Here I have to say, well, in this talk we will remain low, only up to 2, so you can relax. All right. So what are the axioms? Well, I need two objects. First, I need the two category of finite groupoids, okay? Faithful functors between them, these are my one morphisms, and all natural isomorphisms. It's a very easy, nice two category, okay? Nobody is scared by that here. And then I will also need the two category of possibly large additive categories, all additive functors between them, and all natural transformations. These are my source and target. So our definition, sorry, I have a problem with the repeated clicks. So our definition is that a Mackey 2 functor should be a 2 functor, strict or pseudo, it doesn't really matter in this case. M from the opposite of groupoids with faithful functors into add. All right? So opposite means with respect to one morphisms, with respect to two morphisms that really matter, right? They are invertible. And then it should satisfy 4 axioms. Namely, the first axiom, which will not surprise anybody, I hope, is the additivity axiom, where we want a disjoint union of groupoids to be mapped equivalently to the Cartesian product of the categories. I wrote a direct sum because these are additive categories, so it's a Cartesian product and also a coproduct. It's a direct sum of categories in add. And then it follows also that the empty groupoid goes to the 0 category. All right? And why do we do that? Because groupoids decompose in groups up to equivalence, and we only really care about groups. And so the whole information of M is encoded by what it does to groups, group homomorphisms, and the conjugation relations between the group homomorphisms, or group, in fact, injective group homomorphisms. All right? So far so good. Now, what else? Well, we want nice inductions. So the functoriality coming with the 2 functor is what I would call a restriction, and this is induction. So the induction axiom says for every faithful morphism of groupoids, the given restriction functor from M of G to M of H, if the morphism went to H, from H to G, then what I would call I upper star, the restriction along I, has a left adjoint IL and the right adjoint IR, okay? And no, these adjoints are not really part of the structure. I mean, I could add them, and I will add them at some point, but you know, they are uniquely, as you know, there's a uniqueness to these adjoints, so I can forget them whenever convenient. And then I will ask that actually these two adjoints are isomorphic. And so there exists an isomorphism of functors from IL to IR for any I. So this, you will note, is kind of easy to check in examples, right? Just the existence of adjoints, existence of an isomorphism, right? But one of the nice things you can do up to the 2 level, and maybe you cannot do later, I don't know, is that you can prove a strictification, or in this case we call it rectification theorems, saying that under the 4 axioms, including the next one, in fact, if you have like any bunch of isomorphisms like that, then there are unique canonical ones, which I call theta I for every I, which do the same job but better. So they satisfy a long list of extra conditions. So they give you that the left adjoints and the right adjoints define the same pseudo functor by mates and so on and so forth. And so maybe you want to concentrate the 2 adjunctions on the same functor, say the left one, let's call it I lower star, and then you condense the 2 adjunctions on that, you put them on the same functor for every I. And I will not give you the list of properties, but later I will tell you when I use these extra properties, these nice thetas, which come from the axioms, okay? You don't need any special model to tell you that these thetas exist. Okay, now one last axiom, which gives the name to the theory, is the Mackey formula. So this is going to be a base change formula. Namely, if you have an isocomma square gamma of groupoids, so basically a homotopy pullback or a specific algebraic model for it, then let's write it here like this. So you have this given 2-cell here that makes it commute. And then using the adjunctions, you can get a mate like this or a mate like this between the restrictions, right? So here I forgot to put the, sorry. You see, you can restrict along P and then induce using the left adjoint along Q, or the opposite, you induce along I with the left adjoint and then restrict along J, and then taking left mates of this gives you a natural transformation from top to bottom, okay? And then if you first invert gamma and then do the other mates with the right adjoints, you get something that goes up. And we ask by axiom that these two are invertible for every I. These are natural transformations between certain functors, between certain categories. They're not invertible a priori, you want them to be invertible. And that they will give you isomorphisms, canonical isomorphisms like that, which only depend on the chosen adjunctions. Now, the convenient fact is that via the rectification thetas, these canonical identifications of left and right adjoints, in fact, the two mates become mutually inverse to each other. Now, if you are used to doing correspondences in algebraic geometry or anywhere, this never happens. Like you have some mate which is invertible, but you don't get for free a formula for the inverse, right? Sometimes you see it explicitly, sometimes not, sometimes it's just impossible. Here, it's part of the machine. You always know how to construct the inverse to these base change maps. And well, let me give you, for those who have never seen this, let me give you the motivating example of these isocomma squares.
Sorry, can I ask you?
Sure.
You could basically require only, if you say IL, like the left and right adjoint are the same, you could only require one.
No, because the rectification is a consequence of this axiom. So base change, you need left base change, right base change, and some identification of left and right adjoints for all I. Then you can prove rectification. Or you could require the canonical map. Well, the canonical map theta, even before you prove it's invertible, just to construct it, you do it by induction on the order of the groupoids using base change maps. So it's a bit subtle. It's a non-obvious thing.
You are saying there are two double coset formulas, but
yes.
there are because one is with the left adjoint.
Yes, but you can only prove it a posteriori once you know that they actually are invertible. Yeah. I mean, in the examples, you can say more stuff, but at the axiomatic level, you don't know. But yeah, once you have the four axioms, the fourth of which says both are invertible, then you will prove that they are actually mutually inverse. All right, so let me give you an example of an isocomma square. If you take two subgroup inclusions, K and L subgroups of G, then the isocomma construction, this homotopic pullback, gives you a groupoid. It's not a group anymore, basically never, but you can decompose it in a non-canonical way as a disjoint union of these shifted, conjugated, shifted intersections. So it's a typical double coset formula. It's the one that gives you the Mackey formula whenever you see in nature.
That should be I/J right there on the right side?
Yes, thank you. Yes. F was not originally faithful, the first version of the slides. Thank you, that's J. All right, so this is the motivation for having this fourth axiom, and because we have these examples here for groups. All right, so now just a quick look at what actually happens when you reduce all the information to finite groups, as I indicated, thanks to the additivity axiom. Then you have a restriction. Well, let's decompose a bit further. These are only injective group homomorphisms, right? So you have subgroup inclusions and conjugation homomorphisms. Well, you have isomorphisms too, but let's remain a bit simple. Yeah, it's a bit of a cheat here, but in nature, if you do this for a fixed finite group at least, you get restriction functors, conjugation functors, some nice induction functor, which you can choose the functor, but then the adjunctions are canonical and beautiful and uniquely so. So that's another piece of the structure, these adjunctions. And then you have also, not to forget, conjugation natural isomorphisms between certain composites, like these ones. You can restrict and conjugate, or you can just restrict directly to the conjugated subgroup, and then you can canonically identify them. This is very important. It doesn't appear in my later slides, but it's really the complication, what you have to keep track all the time and you don't want to do explicitly. But it's built in the machine, okay? Now, You have many relations, which are complicated to write down, but you also get, in particular, this Mackey formula, which concretely looks like that, as you have probably seen in nature. But again, you don't want to use it like this. I mean, this is a certain way of identifying certain sums of composites. I mean, they are functors, right? This is a natural isomorphism. You want to hide this in the machine, and that's what we do. All right. So there are also further abstractions I will mention briefly, just to keep track of the examples later on. They don't all fit in that framework, but you can say that a Mackey 2 functor is a 2 functor M from G up to A, satisfying the same axioms, same 4 axioms, where now G, the source, is some more general extensive 2-1 category, and the target A is some more general additive 2 category. I don't want to go into details, but if you have already heard, if you know what an extensive category is, maybe you know that you can always do the ordinary category of Mackey functors on an extensive category. If you know what additive means, you probably know what an additive 2 category should have, like some direct sums of objects and one morphisms and sums of maps, you know, everything nicely preserved. So no mystery there. And then also a slight further abstraction, that's more important actually. You may want to require inductions for i's which belong to some special class, which I call J here, J in G, some class of 1 morphisms. It could be all, it could be only the faithful ones, or even less. You know, you can calibrate whatever you have in the examples. That's also not a big deal. So for example, if you want to have a Mackey 2 functors for a fixed group, like maybe you are more used to, let's call it G0, this top biggest group you want to look at, and then you only want to look at subgroups, then you can take G to be the same as J to be the same as the comma 2 category. So you take groupoids and faithful morphisms, comma 2 category over this fixed group G0, and this turns out to be just equivalent to the ordinary 1 category of finite left G0 sets. And that's how they arise in this context, right? Or you could change A, and A could be any suitable 2 category of categories, for example, which it could be, you know, the abelian categories, exact categories, linear over some base ring K. They could be triangulated, or if you don't want your triangulations because you don't like them, then you can take, you know, additive derivators, table derivators. They form nice 2 categories, which are additive in my sense. And also you always stop only at the 2 level, okay, with any of these choices. So that's fine. All right. Now let's see some examples. So there are machines that produce examples, but I don't want to talk about them because you can maybe kind of guess them. And anyway, the axioms are easy to check. That's what I want to say. Once somebody has proved that you have, I don't know, ambidexterity, then you know there is an isomorphism between left and right adjoints. So the axiom is checked. All right, so each of the following families of categories M of G, where you can vary G among, say, finite groups, defines a Mackey 2 functor. So our original motivation was from a representation theory, and maybe I should say linear representation theory, where you look at, you know, just linear representations over some field K or commutative ring K. So you can have the abelian category of representations, or its derived category, or it's stable category, so these are triangulated. And then you have the rest of the structure. It's well known, it's been used for a long time, very useful, and it gives you examples. Or if you want to do representation theory in a more formal way, you can also take Mackey functors like ordinary abelian group valued Mackey functors for the group G. They form an abelian category, and then you do it for every G, and you get a Mackey 2 functor. So that's also nice. You can take cohomological Mackey functors instead. You can do all sorts of variations. So that's nice. Or if you're a topologist, then you can look at the stable homotopy category, the equivalent version. So for every finite group, you can look at genuine G spectra. And at the level of homotopy categories, you get this structure. Okay? Or you can have variance. I guess you can imagine, whenever you have the crucial property here, which is not, let's say, obvious, is ambidexterity. The axiom that says left adjoints and right adjoints are isomorphic. But whenever you have some kind of equivariant spectra which satisfy ambidexterity, you get an example of a Mackey 2 functor. Or actually, my first example was this equivariant Kasparov theory of G sister algebras. It's a triangulated category. You can vary the group G, gives you an example. Or if you're a geometer, you can look at, you fix some locally ring space X, you let a fixed finite group G0 act on it by morphisms of locally ring spaces, and then you can, for every subgroup G of G0, you can look at G equivariant sheaves of OX modules, this abelian category, or you can look at, quasi-coherent sheaves if you have a scheme, or coherent sheaves, or you can look at derived categories, whatever. They give you examples, okay? Lots of variations. These are maybe the main examples that you may encounter. And in fact, funny thing, all of these examples have much more because they are all tensor categories in a canonical, well-known way, symmetric tensor categories. And in fact, they will give examples of symmetric green 2 functors. And they will also act on some Mackey 2 functors and so on. So let me explain what I mean by a green 2 functor. Now this is also a not so complicated definition. So a green 2 functor is just a lifting. So it's a Mackey 2 functor M, which comes equipped with a lifting along the forgetful 2 functor into the 2 category of pseudomonoids in AD. So pseudomonoids, strong functors, strong pseudomonoid morphisms, and monoidal 2 morphisms, whatever they're called, which here means just monoidal additive categories, strong monoidal functors, and monoidal natural transformations, or you could take any suitable additive symmetric monoidal 2 category A as a target, and then you also have such a 2 category of pseudomonoids, right? And then you want them to satisfy one axiom, only one, which says that you have projection formulas, which means here you can construct 4 horizontal maps, which I call R-proj, R-proj, L-proj, L-proj. The 2 R-proj are constructed using the right adjunctions, and the 2 left-proj are constructed using the left adjunctions for every I. And you want them to be all invertible, okay? All 4. Now, if you put the canonical identification between left and right adjoints here and here, I want to say that these things commute, but it's a bit cyclic. How does it commute? But it does. Again, when these 2 are invertible, then this commutes, and when these 2 are invertible, this commutes. It follows from the rectification theorem also. So then there are variations. You can have a braided or symmetric green 2 functor simply by looking at braided pseudomonoids or symmetric pseudomonoids, so, which means in the end braided monoidal additive categories or symmetric, okay? And so all of the previous examples are symmetric green 2 functors. So some remarks. As I already said, these 2 squares are commutative, meaning that the canonical ambidexterity isomorphism theta really identifies the left and right projection isomorphisms. This is, again, very nice and has lots of applications because you can really keep track of what happens, and it's the best possible projection formulas you can have. Now, why the projection formulas? Well, conceptually, I think you should realize that the projection formulas hold if and only if the external products, which look like this, you have them for every pair of groupoids G1 and G2, they go like this, and you always have them associated with a given lift. Huh? The projection formulas hold if and only if these external products preserve inductions in each of the 2 variables separately. So this is maybe the more conceptual formulation of the axiom. You want morphisms of Mackey functions somehow in each variable, and then it transforms into the projection formulas. And why did I start with the projection formulas? Because this formulation of the axiom is not completely general, because you need the source to be Cartesian. But I used faithful morphisms. You don't have products exist, but they don't have the projection. You cannot even construct the external products if you don't have restrictions along non-faithful morphisms of groupoids. But it's kind of a technicality. In all examples you can do this. You just have to change your source a bit. Sure. The left, sorry, I should have said, the left square and the right square are symmetric compared to reversing the order of the tensoring, right? Yes, if you have a braided or a symmetric Green to functor, they are equivalent because the braiding automatically matches them. I had to put them both because in general you don't have a braiding. It's the only reason, sorry. That might be confusing. So there are two meanings of left and right here. The left and right adjunctions, which are the first line and second line, and reversing the order of the tensoring. So the ordering of x and y, if you want, which is the left square and the right square. So in particular, you only have one projection formula, really, if you have a braided Green to functor. All right, so this may be what I said before about external products might give some justification for these projection formulas that seem a bit mysterious at first. But then, let me also point out a bit more terre-à-terre. If we reduce to finite groups, then a Green to functor amounts to what? Well, we have monoidal additive categories M of G for every finite group, maybe braided or symmetric. We have strong, maybe braided monoidal functors. And then we have some conjugation natural transformations which are monoidal. And then they will have to satisfy some coherent projection formulas. And they're left, right, reverse. So that's what you encounter in nature. And you can check the axioms here, okay? At this level. All right, so now I'm done with the axioms and with the examples. Now I'm going to give you results, okay? Can you prove something with these axioms? Yes. Let's see. So, first application, you can use this level of abstraction to produce from examples of Mackey to functors and Green to functors lots of ordinary, abelian group valued Mackey functors and Green functors. That's maybe not surprising. So there is something which deserves the name of decategorification. In fact, there are at least two different ways which are essentially different of decategorifying and get ordinary stuff. The first one is the most obvious. Maybe it goes back all the way to Andreas Dress. It says that if you have a Mackey 2 functor M, which has essentially small values, then you can take K0, right? The additive K0 of each category. The additive functors give you homomorphisms, and the isomorphic functors give you the same homomorphism. So no surprise, if you post-compose with a additive K0, you get an ordinary Mackey functor into abelian groups, right? Or if you vary the target, so if you land in, triangulated categories, you can take triangulated K0, exact categories, you can do the exact K0, or since you're at it, with exact categories, you can take higher Quillen algebraic K theory, right? It's any such decategorification immediately gives you an ordinary Mackey functor. A global one, I should say, okay? Now, another observation, if you have a Green 2 functor, then all its K decategorifications in this sense clearly are Green functors in the usual sense. If only because the previous down-to-earth picture I gave you really looks like, if you forget the isomorphisms, they become equalities, looks like an ordinary Green functor. And the projection formula is one of the axioms for a Green functor, the main one, and that's it. But there is a different way of doing things, a different way of extracting abelian group-valued Mackey and Green functors from our two functorial creatures. And we call it home decategorification. And this goes like this. Let's say you take two objects, x and y in M of G0 for a fixed group G0 or groupoid. Then there is an ordinary Mackey functor for this group, let's say M, which for every subgroup gives you the abelian group, which is the home between the restrictions. You restrict the two objects to G, take home, that's your abelian group. And then of course I have to tell you what the transfers are, what the restriction maps are, conjugation maps and so on. And that's the non-obvious part, of course, but the structure is the only thing you can actually write down in general, okay? It's the obvious thing. It uses the thetas. If you use the thetas to identify left and right adjoints, then you get the axioms of an ordinary Mackey functor. Otherwise not, okay? Now this time I put it inside the theorem because it's really non-obvious, but if M is a green two-functor, and X happens to be a comonoid, so if M is a green two-functor, this guy is a tensor category, and X could be a comonoid in here, and Y a monoid in here, and then this, when you restrict, you still get comonoid monoids by the strong monoidal property of the restriction functors, and this guy has a convolution product, this abelian group. So it's a ring, and in fact M becomes then an ordinary green functor. And you have to prove it. It's not obvious. The projection formula here for the ordinary green functor does not come straight from the categorified projection formula. It's complicated. But it's always true. And this explains why group cohomology, maybe with coefficients, is a Mackey functor, okay? Or a green functor, for example. And you can do, I didn't say it, but you can do global versions. You don't have to fix G0. You can do, if you have a coherent family of pairs of objects, for every G, you can do the same trick. And you get global Mackey and Green functors. Now, yeah, as I was saying, there are variants of these things, and also you can get actions of green functors or Mackey functors. Like, for example, if you are a topologist, you're looking at a genuine G spectrum, which is actually a module over a commutative, say, or I don't know, not even, over a G spectrum, which is an algebra in G spectra, in a highly structured sense, then you will get what? The homotopy groups will give you a green functor acting on a Mackey functor, right? And there are also other ways of getting these things. There's a whole machine here that gives you ordinary abelian group valued stuff. Now, all right, that's very good. And even better, if you look at all the classical green functors, which you know the name of, each of them arises in one of these two ways from from one, or maybe more than one, of the symmetric green two functors that I listed before, or some variant, which was really my motivation to axiomatize green two functors, to explain where all these projection formulas come from, okay? One of these two ways, essentially. That's even better then. You can really recover all the classical examples by unified proofs. All right, that's the first application. Do we have other applications? Yes? That's maybe more closer to the theory side of things, but you have a separable monadicity of restrictions. This means that if you have a Mackey two functor which is idempotent complete, by which we mean each of the valued categories is idempotent complete, of course, and then you take any faithful morphism I from H to G, then, well, you can build this composite between the unit of the left adjoint, right? Then you have theta, and then you have the unit of the right adjoint, and that's going to be the identity. So in particular, for example, the right adjunction here for I gives you a monad which is separated, and so the adjunction is monadic. And the comonad on the left is comonadic, or whatever the terminology is. In any case, you get canonical equivalences between the category associated to H, which is, remember, the smaller group, and the Allenberg-Moore category of modules over this monad, or of comodules over this comonad. So this is maybe not surprising because smaller groups should have easier categories of equivalent objects in some sense. This is a precise way of saying this. You can always reconstruct M of H from M of G plus some little information, which is these monads.
So can you explain how it works when MH is just a category representation of H?
Yes, I can even tell you better with the next bit of the theorem because it uses the monoidal structure. In this case, if M is a green two functor, like the abelian category of linear representations, as you want to know about, well, there is an object which I call A of I, which is basically you take the tensor unit in M of H, and you induce it up. So in the case of linear representations, it's just G mod H, in the left G set, linearized, okay? K square brackets G mod H. But, in fact, it's a Frobenius object in the tensor category. It has a multiplication and co-multiplication. They match nicely. It makes it into, in fact, a symmetric Frobenius object. And the reconstruction of, let's say, KH modules from KG modules happens by taking modules over this ring object, or comodules over the, the comonoid. It's very explicit. You can write down, But it's also true not just for linear representations, but for the derived category or for the stable category, which is highly non-obvious. It's enough to take, rings or co-rings at the level of homotopy category, and it still does the trick. So that's the separable monadicity, which is true really generally. So you might have a question, okay, you have two adjunctions for every I, but you have a unit co-unit composite here, but you also have another unit co-unit composite. So what about the other unit co-unit composite? Is it helpful? Is it the identity? Well, it's never the identity, essentially. But sometimes it's invertible, and it's really useful to know when it is. So let's define the following notion. A Mackey-2 functor M is called cohomological by us if this composite, now what do? We go from the identity of M of G, so the big category, into the right adjoint after the restriction. So you have this unit adjunction. Then you do theta minus 1. You go into the other one. That's the left adjoint. And so you have a co-unit of adjunction. So you see, it's going from here to here, but you have to put M of G, right? Well, sometimes this is just multiplication by the index when H is a subgroup of G. So I use groups because you can say it for groupoids, but then what is the index? So you have to be careful, but it's the same to require it for groups, of course. So if this happens, if this is multiplication by the index, then we call this cohomological. And you might say, all right, but this is weird. Is it actually true? Yes. And you probably know many examples. Here they are. You can take linear representations, so the derived category or the stable module category, or you can even take equivariant sheaves. Okay, any kind of equivariant objects in this sense will satisfy this, but not the stable, the equivariant stable homotopy category. That's not cohomological. Not G-equivariant KK theory. That's not cohomological.
Can I ask? So, is there any general way of describing these self-maps of identity?
Yeah, there are some generalized indices. Yeah. Yes, you can. I will not talk. I didn't foresee it in the slides, but
in this special case, you are asking the distinguish.
In this case, you just want the index as a number, but in general, you have some object which you can use as an index. It's the same object as before. It's A of I. A of I can be seen as a generalized index. Yeah. So what happens? Sorry, that was too far. Oh no. Spoiler. Sorry. Okay, so you have this special result for cohomological Mackey functors, which says the following. Essentially, it says, well, imagine that the index is invertible, right? So multiplication by the index becomes an isomorphism. So you have, again, separable monadicity, but for the other monads and comonads, so you can reconstruct M of G from M of H. So the big group from the small one. And this sometimes happens. So imagine that M is cohomological. Your categories and everything is linear over ZP, meaning here just P is a prime number, and all the other prime numbers act invertibly, okay? And imagine that the values are idempotent complete. So if you take this equivalent stable homotopy categories, you have these, you can implement this easily, but you certainly do not have this, okay? And now take I, the inclusion of a P-silo in a group G. Then you have this separable monadicity and comonadicity, namely M of G now is just Allenberg more objects over this monad or over this comonad. And also for the ring, in the 2 green case, you can do it with a Frobenius monoid. All right, so that was nice, but a bit abstract. So can you reinterpret this in a more useful way? Yes. So my student, Jun Maillard, he looked at that a bit closely, and he can say that, in fact, a Mackey functor, as above, with this hypothesis, is in fact a two-sheaf. So I would say a stack, but it's not a stack of groupoids, it's a stack of additive categories, okay? So it's essentially the same thing. So a two-sheaf for a certain p-local Grothendieck topology on groupoids, or maybe groupoids F, I should say. This was called before by Paul Balmer the SIP topology, so subgroup index prime to P. That gives you the coverings. And so if you translate what it means to be the sheaf condition, you can reformulate it as saying that for every G, M of G is canonically equivalent as a limit of MP, where P runs the orbit category of P subgroups. So you have to take the limit in a pseudo sense inside this two category. But you know, this is far from for being a topological kind of homotopy limit. You know, it's not so hard. You can write down what the objects are concretely, some kind of G equivalent objects, family of objects. You know, everything is quite concrete here. Yeah.
In a way, to follow up to the previous question, so the assumption that M is cohomological, you can imagine weakening the assumption to just
yes.
think that the composition from M of G to M of H to M of G is some kind of equivalent.
Yes, but how do you detect that in the examples?
But there are,
yeah.
I think there are, you can imagine.
There are, yeah, there are. In fact, the next line tells you that there are. Because, in fact, any M admits a two-sheafification for this topology, which is not necessarily cohomological, but which basically, so essentially is given by this formula, right? You replace M of G by this, and you can do it two-functorially in a very nice way, and the junctions come along and everything. That's the hard part. So this guy is almost never cohomological, but it's always a two-sheaf as well, and it satisfies the same formula. By the way, for the stable module category, this was proved by Akil Matthew before us. But this is more general, right? Because you can take, for example, this kind of sheaf categories, or it's also true for the derived category, right? Okay. So there's a whole theory around that I don't want to go into, but there's a two-sheaf point of view on Mackey functors, which is very useful. Yeah?
Try to do some other families of subgroups and three subgroups and stuff.
Yeah, sure. There are variations of this, yeah. All right. So that was just an example of an application. Other applications? Yes. It's going to be my last one. And maybe so far it's the one we are most proud of.
Sorry, may I ask one?
Sure.
I mean, like, I'm a little bit confused about, like, when you take the derived category of KG, somehow, like, I guess the lower formula also holds if you...
This?
Yes. Like, the lower formula, I think, also holds if you just do the infinity limit.
Yeah, exactly.
Somehow you're somehow saying the homotopy, taking the homotopy category commutes with that. I don't know, like...
Yes, what I'm saying is this is a pseudo limit in a certain two category, yes, which happens to give the same result as if you look at the infinity category of additive categories. So there's an underlying infinity category, and then you take the ordinary limit of the same diagram, right?
No, I guess I meant like if you do the derived category and consider it as a stable infinity category.
Ah, yeah, sure.
Then
yes.
The formula is true if you take the limit, but then you're saying like after decategorification, it's still a limit, which is really rare.
I know, that's the remarkable thing. That's what I'm saying. For this kind of, it's really rare. But just before, there's even something more confusing maybe, is that before, when you have this is an equivalence of triangulated categories in the cases where the Mackey functor lands in triangulated categories. It's a separability that makes it possible. It's not, modules in a triangular categories are never triangulated, except...
This limit is also something somehow separable.
Yes, exactly. So this limit, because it lives inside, in fact, this guy is a full no, it's not full, but it lives inside M of Oscillo, and so you can also detect there the triangles and stuff like that. So you can really reconstruct.
Oh, I see, but this idempotent, like in the stable element.
There's an idempotent you can write down, exactly. It's always about, exactly.
Thanks.
Yeah.
So if you take M of G to be the p-local stable homotopy category, the
yeah.
formula is false.
Yeah, because of this condition being cohomological. You have to hit a stable homotopy a bit harder to make it cohomological, I think, and I don't know how to do it.
Well, I know it's not cohomological, but I was wondering if
I don't know.
Right, so do you know that it is false? Is the limit formula false?
I don't know. I think people in the audience are much more, capable of saying if. I just don't know.
I'm wondering if it still holds. That was the point of my question before.
Well, I would be interested in knowing actually the answer to this. Yeah, thank you.
Because that's what I meant. The composition is not multiplication by G mod H, but it's still an equivalent.
Okay.
And one wonders if that's enough.
Well, then, that's a good point. Then well, if it's still an equivalence, you do have that, but I don't know about this. I'm not sure. Can discuss it later. I would like to know, yeah. All right, so I'd like to, let's say, how much time do I have? 10 minutes? Yes. Okay. So for the last application, so this is about things called green equivalences and green correspondences. So there is an original green equivalence, an original green correspondence. This is from the world of modular representation theory of finite groups, and it's about trying to classify the indecomposable representations. And there is a whole theory now, which is already classical. I mean, classical means before I was born, I guess. I don't know how, but from the let's say between the 50s and the 70s, people have developed this theory, and it's been used since as one of the basic blocks, basic things you use in basic things you use in block theory, and in modular representation theory in general. So we set out to try to generalize this and try to export it to other examples than just linear representation theory. So how does it work? Well, first some notations. So if you have let's say a group G and a subgroup P, then I'm going to take inside of M of P the full subcategory, which is going to be again additive, of all objects which are retracts or some induced object up from P. All right? So that's kind of straightforward. Not just induced objects, but also retracts.
So is that supposed to say it's a full subcategory of MG?
I want it to be a full subcategory of MG, by definition.
Sorry, it says MP then.
Oh, sorry. Yeah, that's G. This is G. Thank you. I was looking at it and I didn't see it. Yes, this is G. So inside of M of G, you have these special objects which are kind of coming from P, okay? Up to retracts. And we call them P objects. So classically they call the relatively P projective or relatively P injective. Let's just say P objects. Now, P could be any subgroup, okay? All right, so let's do the same with the family of groups. Anything which up to retracts comes from a group in a given family, let's say X, name of the family, I'm going to call an X object. Now, what can you do with this? Well, I want to look at a group H inside a group G and say, all right, let's see what comes from something lower, some P, which is inside H, and lives in M of H or in M of G. Can I compare to see how much more in M of G comes from P than what comes from H? So induction in steps, right? And there is a very precise way of measuring the difference, which is the theorem, which has the name of green equivalence. So this is the general form of this green equivalence. It's extremely general. So M is any Mackey functor for G. So it could be defined locally just for G and its subgroups, okay? Then I have inside G a subgroup H and a subgroup P. And then let's assume also that H contains the normalizer of P in G. I don't have to, but by doing this, I will get a non-empty statement, okay? I will guaranteed not get an empty statement. Because then, what the theorem says is that the induction functor from H to G gives me an equivalence of categories, more precisely of the idempotent completions of two additive quotients. These are quotients as additive categories, okay? I take same objects, and I kill all the morphisms, a factor through something in the denominator. So I take inside of M of G, I take P objects and kill all the X objects, X for, let's say, I want to excise them. I get rid of them. What are these? Those that come from some self-conjugate of P up to, some self-intersection up to conjugation, where I conjugate with an element of G which is not in H. And then you see that if this condition is satisfied, then P itself is not here, okay? So in general, I mean, in all examples, you get something non-zero in these two portions. So you do this for G here, and you do this for H. And then induction actually goes through, and then you have idempotent complete, sorry. And if you do this, induction gives you an equivalence of categories. Always, okay? Now, it's even better than this, because you never have to idempotent complete, really, because in the examples, if you have categories which land into, say, triangulated categories with countable coproducts, or if you have abelian categories which have the Krull-Schmidt property, or there are some different reasons that tell you that you never really have to idempotent complete. But in this generality, you have to. What can you do with this? Well, classically, what it tells you is that, for example, this was applied to group cohomology. You know, that inside some group cohomology for maybe with coefficients for a big group G, just some kind of stuff that comes via traces and so on. And sometimes you don't want to look at it, you want to quotient it out. Well, you're doing one of these quotients on the right. And you know that if you do this for a smaller group, which maybe you understand better, let's say H, maybe some so-called P-local group, something of this form here, then if you do the same thing, you get the same abelian groups, okay? So in computation, it's quite useful. And in fact, it's also used for something even stronger, namely, imagine that M is Krull-Schmidt. So each of the categories M of G, M of H, and so on, satisfies the Krull-Schmidt decomposition property, so you can talk nicely about indecomposables. And you want to classify the indecomposables in M of G. This tells you that if you look at, well, this kind of purifies into a bijection of those indecomposables in M of G, which come from P. In fact, more precisely, which have vertex P, meaning they come from P, but not from something smaller. This is what vertex means. Sorry, I should have specified. So indecomposables of M of H coming from P, but not from something smaller, are in bijection with indecomposables of M of G coming from P, but not something smaller. Which means you can always reduce questions of classification of, say, KG modules from subgroups of this form, okay, provided you know how to compute your vertex and for each indecomposable and so on. But it's really a simplification of your tasks. Now, again, equivariant stable homotopy does not satisfy Krull-Schmidt, even the non-equivariant stable homotopy, by a famous, in an article by Peter Freid, I think there's a ODT 3.2 or something like that, and it amounts to a sum of two indecomposables isomorphic to a sum of two other indecomposables. So it doesn't work. But again, if you take equivariant spectra and you hit them hard enough, then maybe you get some Krull-Schmidt category that you're interested in, and then you can, thanks to these techniques, you can reduce to smaller subgroups. And let me add, and I haven't prepared a slide for this, but let me add that if you do things P locally, this is very useful because the vertex happens to be a P group usually, and then you have lots of stuff you can do for P groups that you cannot do in general. All right, so I think I will stop here because we want to eat. So let me just tell you that there is more, but that's enough for today. So thank you. These are some references. Very much like?
Mackey conjecture, you know?
The Mackey conjecture?
Yeah, yeah. So number of blocks of D50 of group G is the same as number of blocks of D50. Irreducible representations of block 0 of normalizer of P sub. So it looks very similar like this here, but
I don't know. precisely the statement of this conjecture, but it's about blocks. And yes, and if you look at blocks, you can do similar things, but it's much, much more complicated. So that's something that we have started to do, and we have some results, but you don't have we haven't proved the conjecture for sure, because we are at the beginning of studying block theory through this stuff. So I suspect we haven't proved it by mistake. But you can consider like indecomposable direct factors of these categories M of G, and see how they so blocks, and try to reduce them to smaller groups. And sorry? Ah. Maybe I misunderstood what the conjecture says. I don't know.
Further questions or comments? Yeah.
So have you tried to do a Tambara version of this?
Yeah, doesn't work. I think it's one of those things where at the level of two categories you have serious issues. So we don't know, maybe it works, but we haven't found a way. So there is actually, I have a student who's working on seriously putting as target an arbitrary symmetric monoidal additive two category, and then you can do things like use deconvolution to define your green two functors and stuff like that, and then you can do a bit more systematically things like putting really multiplicative structures in the picture. But I think we are still a long way to actually understanding what the definition should be here. I don't know.
What's the student's name?
Nicola, in the upper left corner.
Okay. So let's thank the speaker again.